before we talk about any kind of algorithm for solving the minimum spanning tree problem, let's make sure we really understand what it is and how it relates to the shortest paths tree concept from the previous lecture. So let's first consider this little tiny graph. And what I'd like you to do is come up with the minimum spanning tree for this graph however you want. So pause the video, think about that, and then I'll show you the answer in just a second. Okay, so in this case, since I have 4 vertices, the shortest paths tree should have 3 edges, and they happen to be the weight 2 edges, and that covers everything that we need. Okay. Harder question. Let's think back to the idea of shortest paths trees. Is there some vertex, my question is, whose shortest path tree is the MST? Remember, the MST is a property of the entire graph, but nonetheless, I want to know, is there some vertex that if you pick it, its shortest path tree is the minimum spanning tree? So think about that. I'll give you a hint in a moment if you're not quite sure what I mean. Okay, so if we look at vertex D and compute its shortest paths tree, so we run Dijkstra's or whatever from vertex D, we would get a tree that includes 3 edges. In this case, it is not the minimum spanning tree, but nonetheless tells you how to get everywhere as quickly as possible from D. Okay? Because it's faster to get to A going straight there via this link 3 edge, as opposed to going the long way, which the minimum spanning tree includes. Okay, so D's shortest paths tree is not the minimum spanning tree. Is there some other vertex for which it is? Think about that if you haven't already. Okay, so if we look at the shortest paths tree for A, we again get a tree, and that tree connects up all of our vertices, but is not the minimum spanning tree. But from B, it does work. So what we see in the middle, this is the shortest paths tree starting from B, and it's also the minimum spanning tree. And then lastly, C and D have the same shortest paths tree, and it's not the minimum spanning tree. So it just happened to work. All right. So to just draw a distinction between what we had last time and what we're doing in this lecture, a shortest paths tree, it fundamentally depends on the start vertex, because what the shortest paths tree does is it tells you how to get from the source vertex to everywhere, and it really matters where you start. However, for the minimum spanning tree, it's a global property of the entire graph. Source vertex, totally irrelevant. There isn't even the notion. Nonetheless, despite that fact, the minimum spanning tree does happen to sometimes be the spanning tree or the shortest paths tree for some vertex. So this I bring up because it suggests one potential algorithm, which would be step 1, find the good vertex. Step 2, run Dijkstra's, and you have somehow, since you've used the good vertex, you now have the minimum spanning tree using Dijkstra's. So what I'd like you to do is think about the following. Given this graph I'm showing here, it's a little funnier shape. First, find the minimum spanning tree, and then second, ask yourself, is there some node whose shortest paths tree is also the minimum spanning tree that you just figured out? So think about that for a bit. I'll spoil the minimum spanning tree in a few secs, but try and think about it. Okay, so it turns out the shortest paths tree for this graph is as follows. It's not unique in this case because there's some values that are used multiple times, but this is a minimum spanning tree. Okay. Now there's another minimum spanning tree, which is we just flip which of these 2s we're using. Either of them work. So there's 2 different minimum spanning trees, but hey, there you go. Okay, now here's another question. Is there some node that if you compute the shortest paths tree, you also get back the minimum spanning tree? Is that possible? Okay, so in this case, you got to be a little clever, but it turns out it is not possible. There is no node for which you compute the shortest paths tree and you get back the minimum spanning tree. So let me just give you an example to kind of give you a sense of why this is true. Imagine we use this bottom left vertex as our starting vertex. Its shortest paths tree, it gets over to this bottom right node next to the convergence point, we'll call it, by going in a straight line. Going the other way, we take all these length 1 edges, and then we hop to the middle, and then we use both of these length 2 edges because we don't want to go the long way, because we're trying to find the shortest path from this purple vertex to everywhere else. And fundamentally, if you think about it, anything you pick over here is going to need to use both of these 2 lines, whereas the minimum spanning tree can only use one of them, okay, on each side. And for that reason, this is not going to get you the minimum spanning tree. And if you use the middle, which I will leave as an exercise for you, you will also see that you don't get it. So you basically have 2 cases, neither of them work, And so what we have here is that the minimum spanning tree is not the shortest paths tree for any vertex. So it turns out that little algorithm I started suggesting, where step 1 is find the good vertex, step 2 run Dijkstra's, it's just not going to work. So we're going to need to do something a little more sophisticated, which we'll do in the next video.